In this video, you're going to learn properties of definite integrals. So in your notes, please go to the next, Go to the next blank spot and title it Properties of Definite Integrals. This is going to be a pretty quick video. There's 5 main properties I'm going to show you. So one thing I want to clarify again is that you remember what definite integrals are versus indefinite integrals. So an indefinite integral does not have a lower and upper bound of integration. When you do an indefinite integral, you're really doing antidifferentiation. You get an antiderivative, which is a function. You have that plus c at the end. If you have lower and upper limits of integration, so like the endpoints on the x-axis, if you're doing area under a curve, that's a definite integral, and you're going to get a number at the end, so it's the exact signed area from a to b on the x-axis. All right, so property number 1 is right here. So you're going to want to write all these down. There's a quick example underneath each, and after each one I'll have a few comments to make, so if any comments are helpful to you, write those down as well. So what property 1 says is if I have an integral from a to b of one function plus or minus another function, what I can do is break it up into 2 separate integrals with the exact same limits of integration. You're breaking it up into 2 areas here. Notice the function f is in the first one, g is in the second one. So basically you're either putting all the functions together, like right here, and finding the total area at once, or you're adding and subtracting those individual smaller areas separately right here. So here's an example for it with actual numbers. Sometimes it's easier to see it with actual numbers and functions. Notice they each get their own dx. That represents the tiny, tiny, tiny width of those rectangles. The second one, if I have an integral and there's a constant k multiplied by my function, you can pull that constant out front and put it right here instead, and it would be the same exact thing. So an example of that is if I have 7 times sine of x and it's the integral of that whole thing, 7 can come out front, and this, when you do just the antiderivative of sine and evaluate it and multiply by 7, it'll be the same as if you had kept the 7 in here. It also makes sense because you're basically using rule number 1 here. Let's say I had the integral of 4x. That's the integral of x plus x plus x plus x, and I shouldn't forget my little dx's here. And using property number 1, if I have a bunch of little areas added together, I can break them up into separate ones where so 2, 3, 4. And 4 integrals ends up being 4 times the integral x dx. So notice I could have just taken the 4 and brought it out front and gotten here without the middle steps. So constants can always go out front. Sometimes it's easier to do the antiderivative and do the fundamental theorem of calculus if those constants are out of the way until the very, very end. All right, here we realize this on that little half shade I gave you. Whenever the lower and upper limit of integration are the same, you do have a height for your rectangle, but there is no width. You're starting at starting at A on the x-axis, and you're not going anywhere. You're still at A. You're not moving. So there's no area. Doesn't matter what is right here. If these are the same, area is definitely going to be 0. Pause the video if you need to get caught up. We have 2 more to go. Property number 4. This one says if I have an integral from a to b of a function, that's the same as the opposite of the integral of the same function, but the limits of integration are swapped. Now remember, when I do an integral, you always do the top minus the bottom. So in this case, this integral would be uppercase f of b minus uppercase f of a, so the antiderivative of b minus a when you plug it in. Here, this would mean f of a minus f of b. The only way for these two to be the same is if you make this the opposite of the whole thing. So let's look at a number line maybe to help make this make more sense here. So if I'm going from a to b and I want this area under the curve, instead of thinking of going from b to a, so like b minus a, if I went from a to b, it's the same exact distance. I'm just going the opposite direction. So let's think about what would normally happen on a number line. If I'm going from 10 to 30, if you do 30 minus 10, so from here to here, that's like this one, you get 20. If instead now you go from 10 to 30, so 10 minus 30, it's the same exact distance, but 10 minus 30 we all know is negative 20. So it's the opposite, same distance but opposite. Okay, so again, if you switch the lower and upper limits, it's the same answer but opposite. And the last one right here, this visual will help it make more sense. If I have an integral from a to b of some function f, and then I have the same exact function and I go from b to c, I could just go from a to c. So look at this picture to help. This first one is from a to b. The second one is from B to C. So this is just saying you could just forget about the little pit stop in the middle and go right from the first to the last destination. Notice that the second one has to pick up right where the prior one left off at B. Okay, so whatever that number is, that number has to be. And I did that here in the example 10 and 10. Sometimes it'll be more advantageous to have it written like this, and sometimes it'll be better to split it up into two separate areas like this. We'll talk about that a little bit later. So we'll practice this in class next time I see you, so make sure you have all those 5 properties written down.